Very good morning, students. So, our today's topic is we are just moving up on the topic ammonia. That ammonia is NH3. So we already performed in the last video lecture about the preparation of ammonia with the help of ammonium chloride, and second is preparation of aqueous ammonia. Now, the preparation of ammonia is done by the process that is very important and known as that Haber's process. And this Haber's process is also known as Haber's Bosch process, because that process is done by the German scientists, both the German scientists, one is Haber, second one is the Bosch. So Haber's process, Haber, the scientist who studied the process of formation of ammonia, that what is the process of formation of ammonia. Okay, the second that is the Bosch scientist studied the effect of high pressure on the chemical reaction, that with the high pressure, providing the condition of high pressure, the reaction goes on a very fast note, the reaction goes fastly. So he studied that effect of that high pressure on the chemical reaction, right? And what are the reactants used in that reaction? So two reactants are there, one is nitrogen gas and second is the hydrogen one. Nitrogen we are obtaining from the air, and hydrogen we used is your molecular hydrogen that is taken, and their ratio is always the fixed amount ratio, that nitrogen is taken as one part and hydrogen is taken in the three part. That ratio is always fixed. Somehow in many of the books or somewhere written as nitrogen hydrogen ratio N2, and it means that its ratio is 3:1. So you get confused with this value, that ma'am it is written as 3:1. So with 3:1 they change their values, that hydrogen is taken as 3 part and nitrogen is taken in the 1 part. That's why they are taken it as a 3:1. Otherwise 1:3 or 3:1, they both the things are similar to each other. But you just remember this thing, that nitrogen is taken in the 1 part and hydrogen is taken in the 3 parts. So that is the introductory part of the ammonia process, that is the Haber process, the formation of ammonia. Now next is about its reaction. So in its reactory part, it is shown that the reaction is N2 is combining with the 3 part of H2. There is a formation of 2 molecules of ammonia plus heat is released out. Why heat released out? Because that reaction of formation of ammonia is always a exothermic reaction, or we can also say that it's a highly exothermic reaction, right? Now, what are the favorable conditions to the reactions to be occur? The very first thing is the temperature. So we always required a temperature of 400 to 500 degrees Celsius or 700 Kelvin. A pressure is required that is above 200 degrees Celsius. A catalyst is used to increase the rate of the reaction, that the reaction goes so fastly, that is finally divided iron, or we are using the iron in the form of a catalyst. And the next is the promoter. The promoter is a substance who is just helping the catalyst, who is just promoting the catalyst to follow the to just work properly and to work fastly. The traces of molybdenum metal is used, and or maybe Al2O3, that is alumina, is used here to just promote the finely divided iron molecules, the finely divided iron particles, to catalyze the reaction that fastly. Okay, and the rate of conversion of the reaction, that almost whatever the reacting substances are present, 15% the reacting material is converting back into our ammonia, that is converting into ammonia particles. But when that rest of the particles are not converting, they again get back into the reactant particles. Abhi we are looking at the diagram, and after looking at the diagram or the flow charts of the substances of this Haber's process, so that we understand properly. Don't worry for that we understand properly. Here in this process, as you look at this diagram, that the very first thing, we have 2 inlets. One for the H2 gas to come in, second is for the N2 gas to come inside the chamber, right? And after just coming in, the hydrogen that is present in the 3 volume, nitrogen that is present by the 1 volume. So we are taking them as 3 volume and 1 volume respectively, and they are taken at a very high temperature. In that compressor part, it is written that it is 20 megapascal pressure. It means that it is equals to 200 into 10 raised to power 5 Pascal pressure. Pascal is also the unit of pressure, and it is almost equals to 200 atmospheric pressure. So we know this thing, that here we required a pressure of 200 atmospheric. So that is the only 200 atmospheric pressure. So this just is simply means that the pressure is 200 atmospheric. Such a high pressure we required. And further, this mixture is passed through an electrically heated chamber, or that is a catalytic chamber. That catalyst chamber is a electrically heated chamber that is coming heated with the help of electrically heated chamber, that is the catalyst chamber is present, right? So we have a catalyst chamber. In that catalyst chamber, that is the your catalyst chamber, and in that catalyst chamber, actually it's, if we talk about, it's the catalyst present that is finely divided iron, or maybe it is present in the form of iron oxide, but we usually take it as in a finely divided iron. That iron is present along with some of its promoters. The promoters may be present as the molybdenum, or may be present as the Al2O3. One of them, the promoters, is present in that case. Now here it is showing at Al2O3 plus water molecule. Okay, now finally here the temperature requirement is around 550 to 500 degree Celsius, that is approximately equals to 700 Kelvin. Okay, that temperature requirements you must have there. And further, the mixture of ammonia formed, that is N2 plus H2 ammonia. In the starting I already told you that the formation of ammonia is an exothermic process. So we required already some cooling pipes, a coolant chamber to cool down the ammonia, and that ammonia is getting cooled down, and that gas is passes through this pipe into this water chamber. That is the water, inside that water is present, and we know this thing that the solubility of ammonia is very high inside the water. That solubility is very high inside the water. So that ammonia is mixed up here with the water molecules, and there is the formation of liquid ammonia. That the formation of liquid ammonia occur, and those, because we know this thing, only the reactant ones, the reactant ones are given here, they can only be converted into ammonia with a value of 15% only. So the rest of the unreacted H2 and L2, they going back with the help of this pipe, and there is a compressor present, that is the pump present, who is just pumping out them back into the compressor chamber, into the compressor part, and from this compressor part they coming back into the catalytic iron oxide Al2O3 water molecules chamber, that is the catalytic chamber, again converting into the liquid ammonia. So that process going back again and again, that it is converted into the completely the N2 and H2 converted into the ammonia particles. Okay, right? And then liquefied, we are liquefying the ammonia first, where the nitrogen and hydrogen do not liquefy easily here, because you understand, you just have a question in your mind, ma'am, when the ammonia gas is liquefied in this liquid, then why the H2 and O2 and N2 is not liquefied? Because they are the gases which cannot liquefy such easily, that's why they are not getting liquefied here. Okay, and the unchanged nitrogen and hydrogen are recirculated, that the recirculation pipe upper portion, that the recirculation pipe is there, so they get recirculated back into the compressor chamber, and from that compressor chamber again they are using for the formation of the ammonia. So that is the formation bar again and again needed, and total that from this process we get 98%. We get 98% of the yield. It means if we are using that nitrogen and hydrogen the 100%, then all of out of 100%, 98% are converted into the ammonia. Almost all the hydrogen and nitrogen are converted into the ammonia, and the ammonia produced is stored as a liquid under a high pressure. That ammonia produced always stored in the form of a liquid at a very high pressure. So that is the complete Haber's process. Just we are looking at the flow diagram for this Haber process. So that is a flow diagram which is showing you about this process, about the process of that your flow chart for the ammonia formation. That is the diagram showing the N2 and H2 compression pump is there within a greater temperature of 200 degrees Celsius above, 200 atmospheric pressure above, sorry, and then electrically heated chamber. Then the mixture is passing through the electrically heated chamber, and then it is passing through the condenser pipe, and finally the liquid ammonia is obtained here. That the uncombined N2 and H2, that is recycled back from this cooling pipe to the compression pump, back into the compression pump, and they are converted into the, they going from this process, okay, completely. Reaction is N2 plus 3H2 converted into 2H3 with the release of a large amount of heat, and the temperature conditions are required at 450 to 500 degrees Celsius, and the pressure conditions are required at greater than 200 degree atmosphere, 200 atmospheric pressure, and the further the catalyst are used are molybdenum and that is your iron. Both the substances are used in the form of the catalyst. So that is a complete process for the process of that is a complete flow chart of the Haber's process. Here we talk about some of the reaction conditions or some of the things that is present in the Haber's process. The very first thing is reaction is exothermic. Although the reaction is a hexothermic process, it means we required a low temperature to proceed down the reaction. But you know what? That low temperature slow down the rate of the reaction. It slow the rate of the reaction. That's why we do not require a lower temperature. We always require a high temperature. And that we provide it a minimum temperature, that is an optimal temperature of 450 degrees Celsius to 500 degrees Celsius, or we can say that it is approximate equals to 700 Kelvin of temperature, because that temperature favors the reaction to proceed into the production of ammonia more and more. And you know what, this reaction is taken up under a very high pressure. Why the reaction is taken up under a very high pressure? Because with that we know this thing, that 4 volumes of that reactant is used, because if we saw the reaction, then 1 N2 molecule and 3 H2 molecules are used. It means total of 4 volume of the reactant molecules are used, and the production of ammonia molecules are 2 only, that the 2 ammonia molecules are formed from this reaction part. So they said that such a high pressure is required to favor the formation of this ammonia, that with the high pressure the ammonia gas formed is condensed down and back into the substance, back into the chamber, and the optimum pressure is found to be taken. That high pressure is provided to be approximate 200 atmospheric, that is greater than 200 atmospheric, or that approximate equals to 20 into 10 raised to power 5 Pascal, or it is also written as 20 megapascals, that the pascals we required here. The next one is the catalyst and our promoters. So the catalyst and the promoters, they are just doing nothing, increasing the speed of the reaction. They are increasing the speed of the reaction. That's why the promoters we the catalyst we used here is the iron, and the promoters is increasing the efficiency of this catalyst. Promoters are helping the catalyst to increase its efficiency. Two promoters used are molybdenum and Al2O3 here, that the promoters are used in this process and in this reaction. Now the last one is the process, that this process is an exothermic reaction and evolved further and maintaining the temperature. Actually, we do not require external heat for this temperature. We are not requiring any external heat from outside. Why we do not require external heating? Because already that process is an exothermic process and heat is evolved. Heat is evolving from this process. If heat is evolving, that amount of heat is completely okay with the requirements of the heat quantity of this reaction. Okay. Next in that, he is talking that the purification of that nitrogen and hydrogen reactants is very necessary. We need to purify this hydrogen and nitrogen reactants. Why we need to purify the hydrogen and nitrogen reactants? Because these hydrogen and nitrogen conductants containing some of the impurities, and the impurities are like your carbon monoxides, that is CO, carbon dioxide, CO2, and traces of sulfur are there. And that substances, that H2S, CO2, sulfur and CO, they are poisoning the catalyst. They are interfering with our catalyst, and if they interfere with the catalyst, it means they decrease down the rate of the reaction. Formation of ammonia को decrease down करेंगे. From that is very essential to remove such kind of impurities from the chamber. So this reaction is all about the reaction of the Haber's process. This is all about the reactory part of our formation of ammonia through the help of Haber's process, through the help of a complete chamber. That reaction is also called as Haber-Bosch process, because both the German scientists worked to define the process. Haber explained you the complete formation of ammonia, and second, the scientist Bosch explains you the high pressure requirements for this reaction, because that with that high pressure requirements, if we study that high pressure requirements, they increase the rate of the reaction, and it becomes very easy to just check down the reaction, and the reaction becomes very fast in that respect. So this is the Haber's process completely with you. This fountain experiment, the second is the fountain experiment. So this fountain experiment is just like the fountain experiment we already performed with the HCl molecule. So in that fountain experiment, the same things are there. That is the water with the indicator that is taken as your red litmus paper. We are taking it as a red litmus paper. Red litmus your solution, that red litmus solution is taken over there. That is a red litmus solution. Again the syringe with water molecule, and that is the water jet, and the dry ammonia gas is present is there, alkaline solution, and that is the fountain experiment. That is a complete fountain is formed here. The same round bottom flask is filled with ammonia gases present with them. The mouth of the flask is fitted with a rubber that is with the help of a stopper with the two holes. The one hole is from the jet of the tube, that is the jet tube present. This is the jet tube present, and second is for the syringe that is containing the water molecules. We are just pumping in the water molecule, and we know this thing that this ammonia, that this NH3 is highly soluble in the water molecule, and there is a formation of aqueous ammonia, that the aqueous ammonia is formed, and the aqueous ammonia, which is basic in nature, it is reacting with the red litmus solution and converting that red litmus solution to blue. What it is doing, just nothing, just converting that red litmus solution into the blue part, that it is converting into the blue part. A trough containing the red litmus solution is present. So that's just the same procedure is there, the same process is there when then outside pressure is higher. When the outside pressure is higher, red litmus solution rushes up through the jet tube. That atmospheric pressure is higher, so it is going up through the jet tube and encourages a blue fountain. That the formation of this blue fountain occur because that red litmus solution is reacting with the liquid ammonia present, that is the aqueous ammonia present. Remember this thing, it is only reacting with the aqueous ammonia present, so it will react with the aqueous ammonia present, and the formation of this process will occur, that aqueous ammonia is reacting with the red litmus solution, and formation of a blue fountain will occur, that the blue fountain is present on that part. Okay, this is all about the fountain experiment, that is completely equal to the same experiment as we already performed in the case of HCl, but the thing is that where we get the red fountain, here we are getting the blue fountain. Only the thing is that